Have you ever stopped to think about the invisible forces all around us, things we can't see or hear or feel, yet they're, constantly interacting with our world? And even with us, how do we even begin to measure something so elusive? Welcome to the Deep Dive. Today, we're exploring the fascinating world of radiation measurement. Our mission, really, is to uncover the ingenious ways science has figured out how to detect and quantify ionizing radiation. We'll go from the basic ideas right through to some pretty specialized tech.
It really is remarkable, isn't it, how we've learned to sense the unseen. And this ability, measuring radiation, it's not just some scientific sideline, it's absolutely critical. Think about safety in medicine, nuclear energy, so many industries, and just fundamental research too. And like you said, it all starts with one core idea, how radiation actually interacts with matter.
Right. And before we dive in, just a quick note. Today's episode is brought to you by AMS Level 3. AMS Level 3 provides consulting, training, and compliance solutions to help companies build stronger, non-destructive testing programs. You can learn more about their services at the link in the video description. Okay, so let's unpack this. If radiation is invisible, how do we know it's even there? What's the fundamental trick? How do you detect something you can't perceive?
Well, the key to detecting ionizing radiation, things like alpha, beta, X-rays, gamma rays, it lies in a crucial after effect. It literally strips electrons from atoms and molecules. It creates what we call ion pairs. And that ionization, that's the signature we look for. That's the handle we grab onto.
Okay. So it's not the radiation directly, but the measurable impact it has. And just to quickly outline, we're talking broadly about what? Three forms? Charged particles like alphas, betas?
Like protons, too. Then you have uncharged particles, mainly neutrons.
Neutrons, okay. And then electromagnetic radiation, X-rays, and gamma rays.
Exactly.
Yeah.
And our senses, completely useless for detecting these directly. So every single detection system relies on specific materials. Materials designed to respond to those ionizing properties. And the responses can be quite different. Sometimes it's generating electrical current, sometimes emitting light, sometimes even subtle chemical changes. It's a really diverse toolkit, but it all hinges on that initial interaction, that ionization event.
Okay, let's start with maybe the most direct approach. Using electricity. Ion chambers seem like a good place to start. It's all about that ionization principle, right? Can you walk us through the basic setup?
Certainly. Picture a sealed chamber. It's filled with gas. Typically, you'll have a central rod, that's the anode, and the chamber wall itself acts as the cathode. Now, when radiation passes through that gas, it creates those ion pairs we talked about. We then apply an electric field across the chamber. This field makes the positive ions drift towards the cathode, the negative electrons towards the anode.
And that movement of charge,
Right.
That's the current.
Exactly. That movement is a tiny electrical current. And crucially, the rate of this current flow is directly proportional to the rate at which ion pairs are being formed. So it gives us a direct measurement of the radiation intensity.
So more radiation, more ion pairs, bigger current. Makes sense. But how do you make sure you're getting an accurate read, like you're actually collecting all the ions created?
Good question. That's all about controlling the voltage across the chamber. If the voltage is too low, many of those ions and electrons just bump into each other and recombine before they reach the electrodes. You lose signal. But as you increase the voltage into what we call the ionization chamber region, the electric field gets strong enough. It efficiently sweeps up virtually all the ions before they can recombine. You get this steady current, a plateau, which gives you that accurate measure of the dose rate.
Okay, but these currents, I read they're incredibly small. We're talking femtoamperes. That's like nothing. How on earth do we measure that?
Yeah, it's a serious engineering challenge. You're right, they are minuscule. So what we do is use very, very high-value load resistors in the circuit. Even that tiny current creates a measurable voltage drop across this huge resistor. Then you need really sensitive electrometers to measure that voltage. Some use specialized components like MOSFETs.
Like tiny electronic switches.
Sort of, yeah, designed for extremely low currents. But another really clever solution, especially historically, was the vibrating reed electrometer. It ingeniously converts that tiny DC signal into an AC signal. And AC signals are much easier to amplify stably and precisely. It was a brilliant way to measure almost nothing.
Wow. So these instruments, do they tell you the radiation level right now or the total amount you've been exposed to over time?
They can do both. Most standard survey meters measure the instantaneous rate, what's happening right now. But many can also operate in an integration mode. They use a capacitor to essentially collect and store the charge over time. This shows the total amount of radiation, the total dose received during that period. And that's absolutely critical for personnel safety, isn't it? Where the cumulative exposure really matters.
Right, like those pen-sized dosimeters radiation workers often carry. Those are classic examples of iteration, aren't they?
Exactly. Take the direct reading dosimeter, for example. It's basically a tiny electroscope. Inside, there's a quartz fiber that gets charged up, making it deflect. As radiation hits the dosimeter, it ionizes the air inside, discharging the fiber. The fiber then slowly moves back towards its zero position, and you can literally look through a little lens on the end and see its position against a scale. It gives you an immediate visual reading of your accumulated dose. Really clever, simple tech.
Okay, so that's ion chambers. Now, what if we crank up that electric field just a bit more? That brings us to proportional counters, right? What changes?
Precisely. If you increase the voltage just beyond that stable ionization chamber region, something new happens. The electrons being pulled towards the anode gain enough energy between collisions to knock more electrons off other gas atoms. You get secondary electrons, then tertiary, and so on. It's a cascade effect called gas amplification.
So it boosts the signal.
It does, significantly. But here's the really innovative part. The size of the final electrical pulse coming out of a proportional counter is still proportional to the initial number of ion pairs created by the radiation event. This means these counters can actually distinguish between different types of radiation based on how much ionization they cause initially. For instance, you could detect alpha particles, which cause intense ionization, even in the presence of beta particles, which cause less. That's a big step up.
Okay, moving up the voltage scale again. Now we get to the really famous one, the Geiger-Miller counter. Everyone knows that classic chirping or clicking sound, right? It's been around since, what, 1928? Still super popular.
It truly is iconic. Simple, relatively cheap. With a Geiger-Müller or GM counter, you push that voltage even higher, beyond the proportional region. Now, when ionization occurs, that gas amplification cascade doesn't just stay localized. It spreads like wildfire along the entire length of the anode wire. It's a complete avalanche, a total discharge within the tube. This creates an absolutely enormous output, pulse volts, not millivolts or microvolts. So large, it hardly needs any sophisticated amplification to be detected.
Huge pulse, easy to read. Sounds great. What's the catch? There's always a catch.
There is. The big limitation is that because the discharge floods the whole tube every time, all output pulses are exactly the same size. It doesn't matter if it was triggered by a low-energy beta or a high-energy gamma ray interacting. The pulse is the same. So GM counters are fantastic for telling you that radiation is present, and roughly how much, but they absolutely cannot distinguish between different radiation types or energies on their own. No spectroscopy possible.
Okay, and because of that huge avalanche, the counter gets kind of stunned, right? For a moment. Explain this dead time idea.
Yes, that's crucial. After that massive discharge, the gas in the tube is full of positive ions slowly moving towards the cathode. During this recovery period, the electric field is disrupted and the counter is temporarily paralyzed. It simply cannot detect another incoming radiation particle. This brief period of insensitivity is the dead time. And it means that at higher radiation rates, the counter will inevitably miss some events simply because they arrive while it's still dead.
And this leads to a really important distinction, doesn't it? What happens if radiation hits during that dead time? Why is this critical for accuracy, maybe even safety?
It matters profoundly, especially in high radiation fields. There are two types of behavior. In non-paralyzable systems, any event arriving during the dead time is just ignored, missed. The dead time duration stays fixed. But in paralyzable systems, which some GM tubes effectively are, an event arriving during the dead time actually resets and extends the dead time period further. This can lead to a really counterintuitive and potentially dangerous situation. At very high radiation rates, the counter can spend more time dead than alive. The observed count rate can actually go down as the true radiation rate goes way up. It might even read 0 if it's constantly being reparalyzed. If you're relying on that meter reading for safety, you could be misled into thinking things are okay when they're definitely not.
Wow, that's a serious pitfall. Okay, what about false counts? Can these things trigger accidentally? How do you stop that? This is quenching?
Exactly. After the main discharge, those slow positive ions hitting the cathode can sometimes knock out secondary electrons, potentially re-triggering the avalanche and giving you a false pulse. Quenching is the process of preventing this. It can be done electronically. The circuit quickly lowers the anode voltage right after a pulse to stop any secondary discharges. Or, more commonly now, it's done chemically. You add a small amount of a quenching gas to the main fill gas inside the tube. Halogen gases are often used today. They absorb the energy, preventing spurious pulses, but then they recombine ready to go again. This gives the tubes a very long, effectively infinite operational life compared to older organic quenching agents that got used up.
And GM counters are really versatile in design, aren't they? I've seen thin window ones for alphas and betas, those flat pancake probes for checking surfaces.
Oh, absolutely. Their design can be tailored. You have end window tubes, side window tubes, pancakes for contamination surveys. And those pocket-sized alarming rate meters you mentioned are common in fields like industrial radiography. They chirp or buzz faster as the radiation level increases, giving an audible warning.
But you have to be careful about the reading, right? You said they can't distinguish energy. So what does the number on the dial actually mean?
That's a critical point. They detect gamma rays indirectly. The gammas interact with the tube wall, creating electrons, which then ionize the gas. But because the response varies hugely with gamma energy, a GM counter inherently measures in counts per minute, CPM. If the meter has a scale in, say, milliengens per hour or microsieverts per hour, that scale is arbitrary. It's been calibrated using a specific radiation source like cobalt-60 or cesium-137. Its reading will likely be inaccurate, sometimes significantly, for radiation of different energies. You always need to be aware of this and ideally consult the instrument's energy response curve or sensitivity data if you need an accurate dose rate.
Okay, that's really important to remember. Let's pause here for a moment. We'd like to recognize Skaggs Media LLC as the creative force behind today's podcast. Skaggs Media specializes in helping businesses build a strong presence on social media through strategy, content, and storytelling that connects. You can find a link to their website in the video description. All right, let's shift gears. We've been talking about ionization in gases, but what if radiation could make something solid actually glow? That sounds like a completely different approach.
It is.
Yeah.
And it's incredibly powerful. This is the world of scintillation detectors.
Mm.
Certain materials, we call them scintillators, have this amazing property. When they absorb energy from ionizing radiation, they emit tiny flashes of visible light, photons. It's a process involving electrons in the material getting kicked into excited states and then quickly falling back down, releasing that excess energy as light, a little spark.
Okay, little sparks of light. But why go this route? What's the big advantage compared to, say, an ion chamber?
The number one advantage is efficiency, much higher efficiency. Think about it. Scintillators are typically solid materials, sometimes liquids, but much, much denser than the gas in an ion chamber. This higher density means radiation is far more likely to interact within the detector volume rather than just passing through. This translates into vastly better detection efficiencies, especially for weakly interacting radiation like gamma photons, or when you're trying to measure very low levels of activity. We're talking potentially millions of times more sensitive than a gas ion chamber for gamma rays.
Millions. Wow. Okay, that's a game changer. So what kinds of materials do this? What makes a good scintillator?
There's quite a variety. One of the most common is sodium iodide, activated with a tiny bit of thallium, written as NaITl. It's an inorganic crystal. Others include lithium iodide, often used for neutron detection, bismuth germanate BGO, various plastics, and even special liquids. What makes a good one? Well, you want high density, obviously. It needs to be efficient at converting the absorbed radiation energy into light. That conversion should ideally be linear, twice the energy in, twice the light out. It also needs to be transparent to its own emitted light, so the light can escape and be detected. And the wavelength of the light it emits needs to match the detector you're using.
Right, the detector. Because of those flashes of light are probably incredibly faint, right? How do you even measure them reliably? This sounds like where the photomultiplier tube, the PMT, comes in. Heard that was a big deal.
It's a huge deal. Revolutionary, really, back in the 1940s. Before PMTs, detecting scintillations often meant someone literally sitting in a dark room counting the flashes by eye. Extremely tedious and limited. The PMT solved that. It takes that tiny flash of light from the scintillator and converts it into a usable electrical pulse. It starts with a photocathode, a surface that releases electrons when light hits it. These are called photoelectrons. Then comes the magic. A series of electrodes called dinodes, each held at a progressively higher positive voltage. When the photoelectrons hit the first dinode, they knock out several more electrons. These are then accelerated to the second dinode, knocking out even more electrons, and so on. You get this electron multiplication cascade stage after stage. The overall gain can be enormous, turning maybe a handful of initial photoelectrons into a pulse of billions of electrons at the output.
Wow, a billion-fold amplification. That's incredible. So the PMT gives you the strong electrical pulse. What happens next? What do you do with it?
That pulse goes into the system's electronics for processing. And here's another key advantage of scintillators paired with PMTs. The height or amplitude, of that final electrical pulse coming out of the PMT is directly proportional to the total amount of light produced by the scintillation event. And since the light output is proportional to the energy deposited by the radiation particle in the scintillator, the pulse height tells you the energy of the radiation that caused it. This is the foundation of gamma spectroscopy. By analyzing the heights of the pulses, we can build up an energy spectrum, allowing us to identify specific radioactive isotopes based on the characteristic energies of the gamma rays they emit. Incredibly powerful for analysis.
Okay, so we've got real-time detection with ion chambers, GMs, proportional counters, and these highly sensitive scintillators that can even tell us about energy. But what if you need to know the total dose someone received over, say, a whole month? Not just the rate, but the accumulated total read out later. This is where luminescent dosimetry fits in.
Exactly. This is a really elegant way to handle long-term integrated dose measurement. The main technique here is thermoluminescent dosimetry, or TLD. It uses special materials that have a fascinating property. After they're exposed to ionizing radiation, they trap some of that energy within their crystal structure, basically storing it. This stored energy stays locked in until you gently heat the material. As it heats up, the trapped energy is released in the form of light. Luminescence triggered by heat, thermoluminescence. By carefully measuring the total amount of light emitted during heating, you can determine the total radiation dose the material had absorbed.
And the go-to material for this, especially for personnel badges, is often lithium fluoride, right?
Right.
Or live. What makes it so suitable?
Lithium fluoride, often doped with magnesium and titanium, is indeed the workhorse for gamma and neutron personnel dosimetry. It has several big advantages. It covers a very wide range of doses. Its response is pretty linear. It can be reused after annealing, heating it strongly to erase the signal. It's quite stable over time. And critically, its response to radiation is very similar to that of human tissue. We say it's near tissue equivalent. This makes it ideal for estimating the dose a person actually received. For neutron detection, you can use life enriched in the isotope lithium-6. Neutrons react with lithium-6 to produce alpha particles, which then deposit their energy and create the TLD signal. You can even use pairs of detectors, one sensitive to neutrons and gammas, one mostly just to gammas, to figure out the dose from each.
So how do you actually read the dose from one of these little TLD chips or badges?
The readout process involves placing the irradiated TLD material in a specialized reader. This reader has a system to precisely heat the TLD according to a specific temperature profile. As it heats, the emitted light is detected by a very sensitive photomultiplier tube. The signal from the PMT is amplified and recorded, typically producing what's called a glow curve, a plot of the light intensity versus temperature or time. The crucial part is that the total area under this glow curve is directly proportional to the absorbed radiation dose.
That's pretty clever. So it's not just for safety badges.
Oh no, TLDs are used much more widely. They're essential in medical physics for verifying doses delivered during radiation therapy. They're used for environmental monitoring, measuring background radiation levels over long periods, and perhaps surprisingly, they have applications in archaeology and geology for dating artifacts or sediments. By measuring the naturally accumulated radiation dose, you can estimate how long something has been buried, a real aha moment, showing how versatile this stored energy idea is.
And quickly, there's a related tech, OSL, optically stimulated luminescence.
Yes, very similar principle, but instead of heat, light, often from a laser or LEDs, is used to stimulate the release of the stored energy as light. OSL dosimeters, commonly using materials like aluminum oxide doped with carbon, are now very widely used in personnel badges, often replacing film or TLDs for routine whole-body monitoring.
Okay, let's tackle the really tricky one, neutrons. No charge, like a photon, but it's a nuclear particle. How on earth do you detect something that doesn't really interact electromagnetically, doesn't directly ionize things?
You're right, the neutron is elusive precisely because it's electrically neutral. It just doesn't feel that electromagnetic force that causes direct ionization. So neutron detection always relies on indirect methods. We have to make the neutron interact with the nucleus of an atom in the detector material in a way that produces secondary charged particles or photons. It's those secondary radiations, recoil protons, alpha particles, gamma rays from capture that then cause the ionization or scintillation we can actually detect.
So you need specific nuclear reactions to happen first. What are the key mechanisms?
Detectors are designed around specific reactions that have a high probability of occurring. Common ones include neutron capture reactions, like Na, where a neutron is absorbed and an alpha particle is emitted, like in boron-10 or lithium-6, or Na, reactions producing protons, neutron-induced fission NF in materials like uranium, or simple neutron capture N that releases gamma rays. You choose the material based on the neutron energy you want to detect and the reaction product that's easiest to measure.
Can we adapt those proportional counters we talked about for neutrons?
Absolutely. One of the most common types of neutron detectors is a proportional counter filled with boron trifluoride gas, BF3. Usually the boron is enriched in the isotope boron-10, which has a high cross-section or probability for capturing slow thermal neutrons via that end reaction. The resulting alpha particle is heavily ionizing and produces a nice large pulse in the proportional counter, easily distinguishable from background gamma radiation. For detecting fast neutrons, you often surround the BF3 tube with a moderator material, like polyethylene plastic, which is rich in hydrogen. The fast neutrons collide with the hydrogen nuclei, slow down, thermalize, and they get detected by the BF3.
Can scintillators help with neutrons too?
Yes, definitely. You can incorporate neutron-sensitive materials into scintillators. Lithium iodide crystals doped with europium, LAI, use the lithium-6 and reaction. Scintillating glasses containing lithium-6 or boron-10 are also used. For fast neutrons, organic plastic or liquid scintillators are very effective. Fast neutrons collide with the hydrogen nuclei protons in the plastic, sending the protons recoiling. It's these recoil protons that cause the scintillation.
And here's another really interesting one I read about. Activation foils. What's the story there?
Activation foils. Another clever integrating technique. It's particularly useful in very intense neutron fields, where electronic instruments might just get overwhelmed or damaged. The idea is simple. You place foils or wires made of specific materials, like indium, gold, cobalt, in the neutron field. The neutrons interact with the nuclei in the foil material, causing nuclear reactions that make the foil itself radioactive. It becomes activated. After the exposure, you remove the foil and measure the radioactivity it now emits using a separate detector system. By analyzing the type and amount of radioactivity induced in the foil, you can work backwards to determine the intensity and even get some information about the energy spectra of the neutron field it was exposed to. They act like a passive recorder of the total neutron fluence.
Moving on to something maybe more modern sounding. Semiconductors. We think of silicon chips in computers. How can these solid crystals detect radiation?
It's a really elegant principle, actually quite analogous to gas ionization. In certain semiconductor crystals, like highly purified silicon or germanium, ionizing radiation can create electron-hole pairs. You can think of a hole as the absence of an electron, acting like a positive charge carrier. These electron-hole pairs are the solid-state equivalent of ion pairs in a gas. By applying an electric field across a specially prepared region of the semiconductor, called the depletion region, you can collect these charge carriers. This movement of charge creates a small electrical current pulse, and importantly, the size of this pulse is proportional to the energy deposited by the radiation particle in the detector.
So, like scintillators, they can do spectroscopy. What are they best for?
Yes, exactly. Their primary and most powerful application is in high-resolution spectroscopy. They offer significantly better energy resolution, especially for charged particles, alphas, betas, and often for gamma rays, compared to most scintillators. You see different types, like diffused p-n junction detectors, surface barrier detectors, and lithium drifted detectors, CDI or GLI. The lithium drifting creates a much larger sensitive volume, allowing analysis of more energetic particles. They are the gold standard for detailed energy analysis in laboratory settings, particularly for low-level alpha and beta counting and high-resolution gamma spectroscopy.
But they're not typically used in, say, handheld survey meters. Why not? What are the limitations?
Right, you don't usually see them in general survey instruments. There are a couple of key drawbacks. Silicon detectors, which can operate at room temperature, have relatively small sensitive volumes and are not very efficient at stopping energetic gamma rays. Their gamma efficiency is quite low compared to a good scintillator. Germanium detectors offer much better gamma efficiency because germanium has a higher atomic number, but they typically need to be cooled to liquid nitrogen temperatures, around a medical 196 degrees C or 77 K, to reduce thermal noise enough to achieve that high resolution. So, the need for cooling, combined with the generally smaller detector sizes and higher cost, restricts their use mainly to lab-based spectroscopy systems rather than portable field instruments.
Okay, makes sense. Finally, let's touch on an enduring classic, something many people working in certain industries would recognize instantly. The film badge. Still crucial for personal safety monitoring, right?
Absolutely. The humble film badge remains a mainstay, especially in fields like industrial radiography. The detection mechanism is fascinatingly subtle. It relies on latent image formation. in the microscopic silver halide crystals embedded in the film's emulsion. When ionizing radiation, like an X-ray or gamma-ray photon or the electron it sets in motion, passes through a grain, it can cause a tiny chemical change, depositing just a few atoms of metallic silver. This invisible change is the latent image.
And the real magic happens during development, right? There's this incredible amplification factor.
It's truly astounding. That tiny, invisible latent image, maybe just a few silver atoms, acts as a catalyst during the chemical development process. The developer solution preferentially reduces the entire silver halide grain containing a latent image speck into metallic silver, while leaving undeveloped grains largely untouched. We're talking about those initial few atoms triggering the deposition of maybe 10 billion additional silver atoms, an amplification factor of 109 or greater. It's this colossal chemical amplification that makes a photographic film sensitive enough to be used for quantitative radiation measurement. That initial tiny energy deposit gets magnified into a visible, measurable darkening of the film.
So the darkness of the developed film tells you the dose.
Essentially, yes. After processing, the optical density, the darkness of the film, is measured using a densitometer. And this density is correlated back to the radiation dose received, usually via a calibration curve. Different filters are often placed over parts of the film within the badge holder to help estimate the type and energy of the radiation exposure as well.
And their role in safety programs is paramount.
Undeniably. Film badges provide a permanent legal record of an individual's cumulative radiation exposure. They are a cornerstone of radiation safety programs and often mandated by regulatory bodies for anyone working with or around significant sources of radiation.
So thinking back over everything, what does this all mean? We've really journeyed from these invisible interactions, particles, stripping electrons, right through to this amazing array of technologies that make it all measurable. From the simple elegance of an ion chamber, just collecting charge, to the classic chirp of a GM counter, the amplified light in a scintillator, the stored memory in a TLD, even that chemical magic in film. Each one tells a piece of this story. The story of how we grapple with, understand, and live safely with radiation.
It really does highlight the ingenuity involved, doesn't it? And the profound impact these measurement technologies have had. It's not just abstract science. These instruments protect workers every day. They guide life-saving medical treatments with incredible precision. They help us ensure environmental safety. And, as we saw, they even unlock secrets about our planet's history and ancient artifacts. It's fundamental to so much.
It really is. So looking forward, as technology keeps racing ahead, what do you think are the next frontiers? Where will we go next in detecting and measuring these invisible forces? How might our ability to see radiation continue to evolve, get sharper, faster, maybe even smaller? And what new possibilities could that unlock for science, for safety, for all of us? Something to think about. Before we wrap up, just a quick reminder that AMS Level 3 is here to support your non-destructive testing needs. Whether it's Level 3 consulting, training, and mentorship, or compliance solutions like NADCAP and FAA readiness, they can help. To learn more, visit www.amsl3.com. That's www.msl3.com. And don't forget to follow our YouTube channel for more insights and updates on non-destructive testing.